Okay, welcome to this afternoon session. The first talk is by Camille, and he will talk about chaos and spatial prethermalization in driven-dissipative bosonic chains.
All right. Thank you, Abhishek. Thank you for having me here. It's always a pleasure to be in Bengaluru. It's a sunny weather. And it's very nice discussions. So I'll be talking about scrambling of quantum information in large-scale quantum devices. And the question is, how can we think about chaos in non-equilibrium quantum many-body systems that are driven far from equilibrium and that are open to an environment, right? So this talk is based on a recent work with these young and bright fellows. So Filippo Ferrari, who is a student at EPFL, and Fabrizio Miganti, who was a postdoc at EPFL and now a scientist at Alice and Bob in Paris. So you all know that for classical dynamics, you have two types of motions. You have the regular motion, right, of the harmonic oscillator, the glorified harmonic oscillators, the integrable systems, and the two-body problem, the Kepler problem. And then for the rest of the world, it's chaotic, okay? Starting from the three-body problem, things are chaotic, right? And the way that one can probe for chaos, at least a dynamical probe of chaos, is to look at trajectories in phase space. So you start your system with some bundle of initial conditions, and you look how they evolve and separate in space exponentially or not, right? And whenever you have an exponential separation, this is a dynamical fingerprint of chaos. This is a Lyapunov exponent that you can measure. And now we're going quantum and to try to understand how we can think of those properties in the quantum setup. So first, quantum mechanically, you in principle lose the notion of phase-space trajectories. But you can first do a semi-classical step and basically quantize this expression using Poisson bracket first, and then you replace the Poisson brackets with usual commutators. And what you find is this square commutator between x of t and p of 0, right? And then if you develop this square commutator, you'll have terms like x of t, p of 0, x of t, p of 0. That's why it's called an out of time ordered correlation function, OTOC, right? And because it's semi-classics, it's going to still follow the same exponential law with the same Lyapunov exponent that is given by the classical theory, right? So people understood how to then generalize those OTOCs. And I'm changing a little bit history, but you can think of how to generalize those OTOCs now to a fully quantum mechanical system. And you basically, instead of working with x and p, you can work with whatever light operator you'd like to, and this is a and b. And you now consider those out-of-time ordered correlators, b of t, that live at different time. Okay? And I mean, this is a very generic picture, but this is what you expect of such an OTOC in a thermalizing system, in a chaotic system. You first expect a rapid growth, okay, that is kind of reminiscent of this Lyapunov growth, a scrambling time, and then a saturation regime, which is controlled by the quantum fluctuations. All right? This growth may or may not be exponential, so you would think that you're guaranteed that it's going to be exponential if your quantum mechanical system has a well-defined semi-classical limit or large N limit. Actually, this is the high energy people that kind of came up with those expressions. And you probably know this bound on the Lyapunov exponent that was derived by Maldacena, where they look at a semi-classical system also, and they put a bound on the Lyapunov using this type of OTOC approach. And the bound on the OTOC is given by the temperature over h bar, which tells you, I mean, this is a very equilibrium system, equilibrium setup, but which tells you that this, the dynamics are kind of bounded by the statistics. All right, so that was time discussion. Let me add space to the soup. So you have now two operators that are living, say, in a two-dimensional space, and one operator is kind of trying to emit something to this Alice, trying to give some information to Bob, but information is spreading in time and in space, actually being lost in the finer degrees of freedom. Right? And this is the so-called growth of operators that you can simply see in that Heisenberg representation of operators, that you have a local operator, and as you evolve time, you represent this Heisenberg evolution as a series of nested commutators, and you see that the local support of your initial operator grows as a function of time. So operators are growing in time. On the same note, you had a very long time ago the Lieb-Robinson bound that was derived a long time ago that basically tell you that two operators are commuting if they're outside of a light cone. And the important message here is that there is a light cone. There is, the fastest object can only move ballistically, not faster than ballistic. Okay, so it cannot be fast. Nothing can be faster than ballistic. At the time, there was no very precise understanding of this Lieb-Robinson bound, of this Lieb-Robinson velocity. It's not a tight bound, but it's telling you that it cannot be faster than ballistic. So it's already some information. And now people are using these OTOC. So here I'm generalizing with space. So now we have time and space. So these functions of space and time to actually understand how information is getting lost, is getting spread. This is the scrambling of quantum information in extended systems. All right. So let me give you a brief overview of what people understood of these objects and these butterfly velocities and Lyapunov exponents in the quantum context. So you can do the harmonic oscillator, the glorified harmonic oscillator, the integrable models analytically. And I wanted to present to you kind of the three categories that I see for those systems that are chaotic, for those systems that are non-integrable. You have the first category is a category of systems that you really are able to do analytical computation exactly until the end, but at the cost of removing some of the physics that you would like to keep. You have problems that you can put on a computer and do exact diagonalization, but typically you're limited by memory and time. And there's another type of approaches which are more like the effective field theory approaches, where you try to coarse grain and have an effective field theory description for your OTOC, but in the doing, you are doing some approximations that need to be controlled. The first example here, the first picture, is the case of the work of Adam Naum and collaborators, where they looked at random unitary circuits. So these are models that are being basically stripped of all the physics except for two ingredients, which are locality and unitarity. And in that context, they're able, so here it's supposed to represent this OTOC, two-dimensional space. And you see that there is this front growing at some butterfly velocity that they're able to compute exactly. So it's a ballistic growth of this front. And they're even showing that this front is broadening diffusively. In this other example, which is ED now, this is a Heisenberg spin chain, 31 spins, weakly disordered. And they also, so this is a spatio-temporal representation of the OTOC. So what you see here is the light cone that I talked about. Right? This is space, this is time, and you see the light cone, and the slope here of this light cone tells you about the butterfly velocity. And these people were trying to argue that in the presence of weak disorder, maybe the disorder is such that it modifies the ballistic spreading to a power law spreading, and this is what they're trying to. But it's hard to say because this is 31 spins. 31 spins is Hilbert space of the billions, but you cannot go very far in time, in 10 time steps. Right? So this is what kind of motivated another type of approach, which is this effective field theory approaches. Presenting him some work with Aditi Mitra and Eric Brunet, based on some ideas also of Aligner, Fauro, and Yoffe in particular, where we now look at thermodynamic systems, so conventional metals in the presence of disorder, and we construct the effective field theory carefully, and we derive the wave equation that the OTOC is obeying. So we can derive the light cone structure, and we can in particular compute the butterfly velocity. We can look at the shape of the front, and we found that in the presence of very weak disorder, clean system to very weak disorder, there is a front which actually opens a discontinuity. So it's a shock wave that's propagating, and after some critical strength of disorder, the shock wave disappears. You have a dynamical phase transition, so the OTOC now belongs to a different universality class of waves, and it now goes to the so-called Fisher-KPP, Fisher-KPP traveling wave equations, where you have smooth fronts with well-defined Lyapunov exponents, etc. And in particular, it allowed us to recompute this very nice relation that gives you a relation between chaotic quantities, which are this butterfly velocity, this Lyapunov exponent on the one side, and on the other side, transport quantity, which is this diffusion coefficient that you have in those correlated metals in the presence of disorder. All right. But now I want to discuss the case of quantum devices. Quantum devices, as you know, so the point is that chaos is not only it's not only a fundamental question. Chaos is maybe also a problem for future application in quantum computing, if we believe in quantum computing, because as these groups are trying to make more and more larger and larger systems with more and more degrees of freedom in the system, with stronger and stronger interactions, because you need nonlinearities in those systems to make them better than just a cold soup. Then this is a recipe for chaos. As you increase number of particles, you're increasing interaction. Chaos is in principle a danger for you. So we wanted to ask those questions of chaos in those systems. And the system that we picked up is one example here from the group of Andrew Houck at Princeton University, where they have, it looks too deep, it's actually a linear chain of resonators. Okay, so these are harmonic oscillators of photons, which are linearly coupled, okay? And everybody is also coupled to a transmon qubit, which basically induces some nonlinearity in the model, right? So it's a Klein-Gordon chain, if you want. It's a quantum Klein-Gordon chain of photons. And because the photons are, you need to manipulate them, you need to monitor them, you need to inject them. So you're coupled to input and output lines, which is basically inducing some dissipation in the system. So the photons, they are not staying there for long. At some point, they escape to the environment. So it's an open system. And because the system is depleting its photon all the time, you need to re-inject photon all the time. So you need to actually bring a drive to the system. That's why you have a driven-dissipative system. So this is a driven-dissipative Bose-Hubbard chain, okay, Klein-Gordon chain, if you want. The theoretical description is given here. So it's a Bose-Hubbard model on a 1D lattice with a nonlinearity here, coupling to the neighbors. This is the drive that brings photons, new photons to the system on the left end of the chain. And because it's open to the world, the dynamics are actually described by a Lindblad master equation. And for those of you who know, this is clear. This is just the decay of photons at both ends of the chain. So we wanted to, so clearly, you expect that this is an interacting system. You're injecting photons, you are dissipating photons on the other end. You expect a non-equilibrium steady state. And the question is, can we expect this system to be chaotic? And the naive answer is, of course, yes. It's a weakly interacting system. The Bose-Hubbard model is a non-integrable model. This is chaotic, and that's fine. And it's not a scoop. Question is, but what do you mean? How do we probe for chaos in a non-equilibrium open setting? So this is more of the interesting question: is how do we actually define chaos in that setting? And then, if we find that indeed this model and this system is chaotic, does it mean that it will eventually thermalize, because chaotic system thermalize? So not thermalize in time, of course, because this is constantly applied on this end of the chain, but maybe it will thermalize in space. Maybe the last site of the chain will thermalize to some low temperature vacuum type of state. And if we believe that it thermalizes, the question is, well, but the route to thermalization, as we know in, say, quenched system, the route to thermalization is hydrodynamic. So you first have some quick relaxation of your non-conserved quantities, and then in principle you have a hydrodynamic regime that takes place until the late thermalization. So can we talk about thermalization in this particular context? And what's the role of chaos here? All right, so that's the roadmap. All right, so that's the only technical slide of the talk. Just to tell you that these systems are rather weakly interacting. These are very large systems, so this is not thermodynamic number of photons, but 72 bosons you cannot put on a computer. Even two bosons is difficult because these are infinite Hilbert spaces at each side. So we definitely need some strategy in order to deal with these system sizes. And the idea was to use the fact that actually, because we have rather large number of photons in the system, because we're driving far from equilibrium, we're injecting a lot of photons. And because the nonlinearity is kind of weak, we're in a regime where things can be described in terms of semi-classics. So we're giving a semi-classical description of these dynamics. The technical thing is called the truncated Wigner approximation. It's basically you replace the quantum operators with complex fields, right, with amplitude and phase, and then you deal with quantum fluctuations with some technology model product. I don't want to enter too much details, but basically the central object of these approaches, of this phase space representation of quantum mechanics, is this Wigner function that tells you that locally at a given, at a given resonator, it tells you the probability that your field is somewhere in the complex plane. And you can find the PDE that is obeyed by these Wigner functions, and after some truncation, consistent truncation in the quantum fluctuation, you map this PDE to a Fokker-Planck equation, and this Fokker-Planck equation, you map it to a Langevin equation, which is here. So it's stochastic field dynamics. Now you have those classical-looking fields that are evolving under, so all the ingredients are here, coupling to the neighbors, interaction, drive, dissipation to the end, and quantum fluctuations. And this is a linear set. Well, the size of this set of equations grows linearly with L. So then you can really start putting them on the computer, and we can go up to sizes of order hundreds. Okay, so it's much larger than what we can do with ED. All right. And this is typically what you obtain in the computer. So these are stochastic trajectories. These are the so-called Wigner trajectories. And then you can look at the statistics of these objects and understand what's going on in your system. So in particular, we want to probe for chaos. And the probe for chaos that we thought of is the following. It's something that can, is the closest that we can think of an experimental proposal. The idea is that, okay, you have a long chain. You can monitor your chain on one end and on the other end. And what we're going to do is to look at those Wigner trajectories at the last site, okay, when we do something to the phase on the first site, okay? So we're going to track this maybe Lyapunov exponent here on the last site when varying the phase here of the oscillators on the first site. So that defines our semi-classical OTOC, right, which is defined directly in the steady state. And it's the variation not of the phase, but of the exponential of the phase, because quantum mechanically the phase is not a really good operator. But it's basically the phase here, variation of the phase here with perturbation of the phase here, right? And this object is this is our OTOC. This is a function of space and time, and this is represented here in that corner. So this is the light cone structure that I was showing you before, but for that particular non-equilibrium many-body system out of equilibrium and open to the environment, where you see a clear light cone structure with a butterfly velocity that we can measure and study. And if we take cuts at, given sites, so here I'm working, say, at site 60, okay, I'm doing a cut like this, and I plot what I see, I will see a very neat exponential growth here. Okay, this is a semi-log plot, a very neat exponential growth, followed by the saturation regime. Okay, so this is what I promised in the beginning. And you can extract the Lyapunov exponent here and study the Lyapunovs. And you can also clearly see that there is actually a traveling front. So this is now for different slices here, different points. And you can see that there is actually a front that is traveling and deformed in the system. So it has a traveling wave form. Okay, so from that and this new diagnostic, we can clearly conclude that as we expected, the system is indeed chaotic. And we can now discuss about it in the non-equilibrium setting. And because this system is chaotic, now we can start asking the question as, okay, but is it then that the system thermalizes, and how? So I will argue that actually, yes, the system will thermalize, and the mechanism by which it will thermalize is actually quite reminiscent of what happens in the time domain when you do a quench. So in that case, I'm going to argue that close to the boundary drive, remember the boundary drive breaks the U1 symmetry of my Haber model. Right? So close to the boundary drive, the U1 symmetry, which I can picture by looking at the Wigner function in the complex plane and seeing that the probability to find my field somewhere in the complex plane is not rotational invariant. So here it's definitely not U1 invariant. But this, and you can also see that the average of the phase, which is this red curve here, is finite. Okay? But after a few sites, quickly, the U1 symmetry is being restored. So the phase, so what we learn is that the phase degrees of freedom are quickly relaxing, okay, to a disordered state. Whereas for the amplitude, this is now the blue curve, the amplitude, it takes a much larger space length to decay to something that is eventually going to be, few photons inside the last cavity. And in between this relaxation phase and the relaxation of amplitude, there is a very long regime that is described by an almost constant amplitude. It rings the bell that maybe there is an effective chemical potential in the system that has built up, and it is maintaining this number of photons at a high level, right? And we can probe for that hydrodynamic description by basically, I'm going very quick here, but by basically putting some local thermometers along my lattice, right, around my sites. I can measure the effective temperature. I can see whether they are thermal or not, whether they are purely out of equilibrium or that they can be modeled by a thermal ensemble. And I can measure the temperature. I can measure the effective chemical potential. Right? And what I will find is that indeed, so in the beginning, close to the boundary drive where the U1 phase is not restored, the one symmetry is not restored, sorry, things are non-thermal, but very quickly, things are becoming thermal. So very quickly in the chain, I have a local thermal description for my non-equilibrium steady state, right? And here I'm plotting the ratio of chemical potential, effective chemical potential by effective temperature. It's an adimensional ratio. And what we found is that basically along the chain here, you have a slowly varying chemical potential, a slowly varying effective temperature. And it's only eventually that the chemical potential will drop down zero, below zero. Okay, so you have at the end of the chain a negative potential, which is trying to deplete the number of photons. But in between those two extremes, you have a long regime that is well described by a hydrodynamic description. We call it prethermal because it's a regime that has an emergent chemical potential which remembers the initial condition. So here the initial condition is a boundary condition. And we checked that this long prethermal phase is actually a phase in the sense that it scales linearly with the system size, up to the system sizes we could test in the computer. And so to conclude, I was trying to convince you that if we're being serious about quantum computers, we should probably also think about quantum chaos in those devices. The same way that classically, there have been a lot of, actually it's a full-blown discipline of doing control of chaos, trying to stabilize some periodic orbits. We should probably try to do the same quantum mechanically. Then I introduced this semi-classical definition of chaos in non-equilibrium steady state open to the environment. And I presented this particular example that happened to show some nice thermalization in space, right? That basically hinges on three ingredients. You break the symmetry with your drive on the left hand of your system. The bulk of the system is symmetric, so the symmetry and the bulk of the system is chaotic, so the symmetry is quickly restored. But because the conservation law associated to this symmetry makes it that the number of photons is hard to relax, so it has to, it's hydrodynamic, so it has to find some way to relax. And here in that system, the only way to relax is through the boundaries. That's the reason why you have such a long scale for the relaxation of the amplitude degrees of freedom. And eventually, you have a full-blown thermalization to some kind of vacuum state plus quantum fluctuation plus a little bit of residual thermal fluctuations. Well, thank you very much.
Actually, so I just had a comment. So actually, very similar model was that Klein-Gordon model.
Yes.
Driven, right, was studied by a Princeton group and also by me, Anupam, and a student.
Okay.
And one of the things we observed, I don't know if you, so in this model, as you change the driving force, like there's a regime where the current remains completely constant, and then, so then it's in a periodic phase, and then it goes to the chaotic phase.
Correct. So yeah, I was hiding this, but so if you drive very weakly, you have very few photons inside your. I mean, in my language, you have very few photons in that setup, very few excitations. So the nonlinearity is not kicking in. So what you actually see is a linear regime, and the OTOC that if you would plot these OTOCs in that regime, you would see a non-exponential growth. So you see a parallel growth, maybe some small oscillation, that would not saturate to the same bound here, to saturating to the maximal. So this here it was saturating to 1, which is actually the maximal value you can get from the definition. And if you are in the linear regime, basically you will get some oscillation and basically a very slow parallel here, and then it would saturate to something else.
No, but actually, even in the strong force
and
regime,
in the very strong, yes,
there's still a periodic state.
Okay, so in the very and the other extreme is also very interesting again, and it's also non-chaotic. So that's why I did not discuss. But if you drive very weakly, it's non-chaotic. If you drive very strongly, it's also non-chaotic.
No, so at least in the model that I know, which seems very similar, there's an intermediate force regime where it's periodic, and for large force and small force, it's chaotic.
It's periodic because you're driving with a periodic drive. So the drive is a periodic drive, I guess.
Yeah, the drive is a periodic, which is.
So here it's a constant. It's a constant drive, but.
Yeah, maybe we can discuss later. Yeah, other questions?
So when the drive is very weak, I guess semi-classics will break down, right? Because you have very less photons in the system.
Correct.
So,
but still, the argument holds. I think the fact that you're not activating the nonlinearities if you have very few photons. So then, I mean, the Bose-Hubbard is just a tight binding model. If you don't put.
So it's basically just a.
It's a glorified harmonic oscillator.
What sets the scale where the amplitude equilibrates? How does that depend on the drive? The next plot, yeah, this one.
Here?
Yeah.
Yeah. So this is a complex number. I mean, complex in the sense that this takes into account how you drive, how you dissipate, and the balance between, and also the nonlinearity. So basically, these rings that you see here is and the radius of the ring is precisely this number. This ring is really a Mexican hat. So it's the competition between the quartic interaction and of the Hubbard U and the quadratic terms of the oscillators and the effective
Questions. I had one more question. So finally, I mean, you have like in the semi-classical description, it's basically a classical equation. So in that case, why does it saturate and why doesn't the exponential growth go on forever?
So I should have mentioned. So it's a semi-classical equation, but quantum mechanics is still hiding. It's still hiding actually in the initial conditions. So the initial conditions are sampled. I didn't say, but I should have said that the initial conditions are sampled in some ensemble that is where quantum mechanics is hiding. Quantum mechanics is also hiding, I think, in the noise.
But so this prethermal state can be understood from the fact that you are close to an integrable point or not?
No, far from integrable.
Because U is small, right?
U, okay. But U is small, but as soon as if you have a thermodynamic system, as soon as U is epsilon, you are non-integrable.
Yeah, that's true, but you need the time order 1 over U square or some power of U to see it. Right?
Yeah, but we wait for long. So this is directly in the non-equilibrium steady state. So we wait for the non-equilibrium steady state to form. So things have traveled a lot, and the systems are pretty large. So I think we're far from integrable, even though U is weak. Except if you really drive slowly, then if you drive very weakly, then. Okay.
So then, what's the origin of this two-stage? You don't know.
The two-stage. Well, you have my understanding is like you have your braking symmetry. So the U1 phase is non-conservative, so it quickly relaxes. But for the amplitude, it's corresponding to the conservation of photons. This is a hydrodynamic relaxation, so it has to find some way. It's conserved in the bulk, so it has to find some way to relax them. And this is at the boundaries of the system that it can relax. So that's why it takes so long. So then you have those two relaxation scales that are very separate from each other. And then in between you have room for, so first it's chaotic, and then you have room for something emergent, which is this hydrodynamic regime.
Okay, so if there are no other talks, let's thank Camille.
Long live India and France friendship.